Thank you, Professor Guerin, for the wonderful talk. Our audience had some questions today based on the presentation. So I'll just proceed with them if you do not mind.
Yeah.
So our first question comes from a faculty member who has been attending this session. So the question is whether you can elaborate on the relationship between the monoclinic angle in the crystal and the piezoelectric response observed, and what is the origin of such a relationship?
Yeah, so we have two components to a piezoelectric response. We have our polarization tensor, which is our kind of Coulomb per meter squared value. And then we have our elastic stiffness tensor, which is a 6 by 6 tensor from which we can derive our Young's modulus and all of those kind of bulk properties. In order to get your, I suppose, core piezoelectric constant, our picocoulomb per Newton value, you're dividing those two values by the other. So you're dividing your polarization tensor by your elastic stiffness. So that's why I was saying that your piezoelectricity is inversely proportional to the flexibility of the material, or the more compliant a material is, the more piezoelectric it's going to be. So if we have a monoclinic angle in our unit cell, that means that by symmetry, you can have 5 different shear piezoelectric components. And if the monoclinic angle is quite large, then that means that your shear stiffness is going to be very low. That means your C44, your C55, and your C66 are going to be very small. Generally, we see them between about 1 and 5 gigapascals for a flexible material. And then and then our piezoelectric output is the ratio of the polarization to the stiffness. So if we have a monoclinic angle and a monoclinic crystal, that tends towards having low C44, C55, C66, which means that our shear piezoelectric response will then be higher.
So, Dr. Guerin, I have a query. I'm not sure if it's correct. So,
Okay.
technically, the monoclinic angle should be changing the domain populations of the dipoles or charges. And does that also play a part?
Absolutely, yeah. So for some space groups, you'll have a naturally occurring dipole at equilibrium if it has a longitudinal response. But for most crystals, that dipole appears when you actually apply your displacement. So for your monoclinic crystal, yeah, it's directly related to what charges appear when those molecular dipoles are distorted. And if there's a monoclinic angle or any angle in the unit cell, you're going to get larger ionic displacement, larger movement of molecular dipoles, and an increased response.
Thank you, Professor. So, my next question has to do with the types of structures like zero dimensional, one dimensional, two dimensional, three dimensional that are generated from, let's say, as an example, the piezoelectric amino acid crystals, and whether the dimensionality has any relationship with the properties.
That's a great question. Yeah, we haven't worked too much with lower dimensionalities of materials. We have done one collaborative study where we did see that reducing the dimensions in that case increased the piezoelectric response, but I don't think we've done enough, I suppose, systematic studies to definitively say if there's a direct effect. But I suppose the problem in 3 dimensions is the more complicated your structure, generally the more dipoles that are going to be in your unit cell, and the more cancellation you get of that response. So even if you have a molecule with a very large dipole, that's not enough to predict its piezoelectricity. You need to see how those molecules pack together in 3 dimensions. So when you're able to reduce the dimensionality down, you tend to increase the orientation, reduce interfering anisotropic effects, and get more piezoelectricity. But that's still very small level. We need to study more 2D, 1D structures to say that.
Thank you, Professor. So our next question has to do with the synthetic methods for these crystals. Has it been possible to get the same crystals through different synthetic methods, such as solid state reaction or solution phase synthesis, or say single crystal to single crystal transformation? And have there been differences in the properties based on the method of synthesis?
Hmm. Yeah, that's a great question. I mean, piezoelectricity it's a bulk single crystal property. So in theory, no matter how you obtain your crystal, the properties should always be the same at the single crystal level. Unless there are some very cool studies that have literally come out in the past couple of months that have looked at crystallizing in magnetic fields, crystallizing in electric fields, that definitely for polycrystalline samples creates that orientation. It's the equivalent of poling, what we do with ceramics, to do that. But no, in theory, no matter how your crystal is made, you should get the same properties every time. And in the polycrystalline phase, if you can synthesize those materials with increased orientation of each crystal, you should get an amplified response.
Thank you, Professor. Our next question has to do with energy and power generation from piezoelectric crystals. So, uh, we were wondering what's a good way to measure efficiency when it comes to power generated through piezoelectric
Mhm.
devices or films or crystals.
Yeah. Yeah, so in that case, I mean, I talked a lot about voltage today, but a problem with piezoelectrics across the board is low current. So in terms of engineering these materials, you really need to look at amplifying the current generated. We're doing that currently with kind of large arrays of piezoelectric materials or piezoelectric transducers in various configurations that can amplify the current and then bring up your power. Um, Efficiency is a hard one. I mean, really, it's about kind of fatigue testing, it's about cycling, it's about repeated application of force over time. You can get the single crystal efficiency from measuring your electromechanical coupling coefficient, which you can get from impedance analysis. So that's a K squared, and that gives you a rough idea of the electromechanical conversion efficiency inherently to your material. But for the macro scale applications, I think it's just, yeah, normal kind of cycling and fatigue testing to see what the material can withstand mechanically. But yeah, then also if you're getting any loss of signal. But we found that once you don't damage your crystal, the properties are maintained no matter how much stimulus you apply over time.
Thank you, Professor. The next question has to do with the coating or deposition method. So, is there an impact that you have observed in the laboratory as to the use of the exact, because there are multiple coating methods. The easiest one is, of course, spin coating,
Yeah.
or the what they call as the doctor blading or drop casting method.
Mhm.
Of course, there are other coating technologies available, methods available.
Mhm.
So the two questions here is whether the method of coating has mattered for
Mhm.
your group's crystals, and the other question is whether there is such a thing as an optimal film thickness.
Yeah. In terms of techniques, so it's Tara Ryan and my group, her whole PhD is these polymer coatings. So right now, because we're trying to coat those, you saw the discs and the plates, we need three-dimensional uniform coating. So for us, it's been dip coating, seems to be the most successful, where you're submerging your crystal component into your solution and then removing it very, very slowly at a particular rate, and then you're rotating it and covering it again in that same bath. Spin coating is very difficult to get uniformly around our entire device. Is challenging for us, but yeah, so dip coating is what we found has been best. That's what we did in the study that I showed. And thickness is what we're looking at right now. We're looking at seeing, is there a thickness piezoelectricity relationship for our coating. So our first goal was to make it insoluble, and now we're looking at optimizing the coating parameters and the thickness to see if that has an effect on the properties themselves.
Thank you, Professor. So the next question is based on the crystallinity, because all of the materials that have been displayed so far are crystalline. But in theory, if it's based on if the property of piezoelectricity is based on the distribution of molecular dipoles, can it also be achieved in amorphous
Mm-hmm.
materials?
Yeah, it's really interesting because yeah, we're very much like, yeah, solid state physicists and chemists. So far we've worked with purely crystalline materials. But you can absolutely, like, as in people, you know, make pellets and powdered pellets and things like that, from less crystalline phases. But I suppose the answer is I'm not sure. I mean, we haven't looked at it in amorphous materials. Our understanding of how this property comes about is through our solid state crystal theory. But you know, molecular crystals or molecular materials have lots of surprises. So I won't definitively say yes or no, but we haven't studied amorphous materials yet to see if it's there.
Um, Thank
Uh,
you, Professor. So I'll just
okay.
hand it over to Neha for conclusion.
Thank you so much, Kaushik. I was about to come to it since we are a bit tight on the time, so we won't be able to take up any more questions. And thank you, Dr. Guerin, Dr. Kaushik, and Dr. Manas for collating the question and answer session. Thus, on behalf of all of us at ACS, thank you for joining us today. We hope to see you again soon for more ACS webinars and events. Until then, stay safe and stay healthy. Thanks to all the audience for joining